Hello there and welcome to Learn When You Sleep. Tonight we drift into the long, golden world of summer, a season that reshapes the planet in ways most of us never pause to notice. When the air warms and the light stretches far past the hour when darkness used to arrive, the ordinary world becomes something slower, softer, and stranger. Summer is not simply warm weather. It is a transformation written into the very chemistry of the atmosphere, the biology of every living thing, and the physics of light itself. A season where heat unlocks hidden processes, where the air hums with forces that stay invisible in cooler months, and where the planet tilts just far enough toward the sun for its deeper workings to come alive. There is something almost suspended about summer, as though the world has been given extra time to reveal what it is made of. Beneath the stillness of a hot afternoon, beneath the weight of thick air, beneath the long, slow dimming of a summer evening, extraordinary things are happening quietly in every direction. If you enjoy these slow journeys into the science of the world, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, just breathe. Let the warmth settle around you. Allow your thoughts to loosen and your body to grow heavy. And let the long, quiet haze of summer carry you gently towards sleep. Let us begin. Summer sunlight travels through more chemistry before it reaches your eyes than most people ever consider. When the sun rises high in a summer sky, its rays enter the atmosphere at a steep angle and pass through a relatively thin column of air. Along that path, they collide with nitrogen and oxygen molecules, with dust particles, with droplets of water vapor, and with trace gases that shift in concentration through the season. The blue end of the visible spectrum scatters most strongly during these collisions, spreading outward in every direction, and filling the dome of sky with the deep saturated blue that feels so characteristic of summer. At the same time, ultraviolet radiation increases significantly because the path through the atmosphere is shorter and the sun spends more hours above the horizon. This extra ultraviolet energy drives chemical reactions in the upper layers of air, breaking apart molecules and reassembling them into new compounds. Ozone concentrations fluctuate in response. Particles released by vegetation react with pollutants to form haze that gives summer afternoons a particular milky quality in certain regions. Every breath of summer air carries a chemical fingerprint shaped by the angle of the sun and the length of the day, a mixture that does not exist at any other time of year. Warm air holds a different relationship with sound than cold air does. In summer, the ground heats quickly during the day and transfers that warmth into the air immediately above it. The air higher up remains cooler. This means sound waves traveling outward from a source encounter layers of air at different temperatures. When a sound wave moves from cooler air above into warmer air below, it bends upward rather than curving back toward the ground. The practical effect is that sounds seem quieter at a distance in summer than they do in winter. A voice calling across a field, a train crossing a distant bridge, the low rumble of thunder from far away. All of these sounds disperse upward into the sky rather than traveling along the surface. The atmosphere absorbs them and they fade faster. This is why summer nights, once the ground has given up some of its heat and the temperature layers become less extreme, can feel acoustically different from summer days. The world sounds slightly more open after dark in the warm months, not because anything has changed in the landscape, but because the invisible structure of the air has rearranged itself slightly, bending sound along new paths. The color of the sky during summer twilight is shaped by forces operating hundreds of kilometers above the ground. As the sun drops toward the horizon, its light travels through an increasingly thick slice of atmosphere. More molecules, more particles, and more layers of air separate the sun from the observer. The shorter wavelengths, the violets and deep blues, have already scattered away long before reaching the eye. What remains is the warm end of the spectrum, reds and oranges and golds that wash across the lower sky in bands that shift and deepen over the course of many minutes. In summer, this process is extended because the sun moves along a shallower arc near the horizon at higher latitudes, lingering in the transitional zone between day and night for longer than in other seasons. Twilight can last for an hour or more. The sky cycles through colors that have no name, blending from orange to rose to a deep saturated violet overhead that slowly deepens into blue. Thin high clouds catch this tinted light and hold it after the lower sky has gone dark, creating streaks of color that seem to float above the landscape long after the sun has set. Summer changes the way that color appears on every surface it touches, not because the surfaces themselves change, but because the quality of summer light is different from light in any other season. The sun in summer sits higher in the sky than at any other time of year, and light arriving from a high angle travels through less atmosphere than light arriving at a low angle near the horizon. This shorter path through the air means less scattering, less filtering, and less removal of the shorter blue wavelengths before the light reaches the eye. The result is that summer midday light is whiter and more intense than the warm, golden light of winter afternoons. Colors seen under summer light appear more saturated in some ways and more washed out in others. The blues of sky and water are deeper. The greens of vegetation are more vivid early in the season when leaves are fresh and their chlorophyll is dense. By late summer, when leaves have been exposed to months of intense radiation and their protective pigments have accumulated, the same greens may appear dustier. Shadows in summer are sharper-edged and darker because the high sun creates a more defined boundary between illuminated and unlit surfaces. Photographers know that summer midday light is harsh and unflattering, while the low golden light of early morning and late afternoon is more beautiful. The difference between these two qualities of light is entirely a matter of the angle of the sun and the length of the path its light travels through the atmosphere before it reaches the surface. Heat causes the air itself to become visible in a way that does not happen in cooler seasons. When the ground absorbs solar energy and transfers it rapidly into the thin layer of air directly above the surface, that air becomes significantly warmer and therefore less dense than the air just above it. Light traveling through this density gradient bends and refracts unpredictably. The result is the familiar shimmer seen above hot roads, open fields, and sandy ground on summer afternoons. Distant objects appear to ripple, stretch, or float slightly above their actual positions. Mirages form when the bending of light is strong enough to create an image of the sky on the ground, tricking the eye into seeing water or a reflection where neither exists. These are not illusions created by the mind. They are accurate images produced by real optical physics, the same physics that bends light through a glass lens, applied to air that has been transformed into a refracting medium by nothing more than absorbed sunlight. The shimmer is a portrait of invisible heat, made momentarily visible wherever the temperature gradient becomes steep enough to bend light significantly. Summer nights at high latitudes experience a phenomenon that has no equivalent in any other season or region. When the sun sets but barely drops below the horizon, its light continues to illuminate the upper atmosphere long after darkness has settled on the ground. A faint but distinct glow persists in the north, shifting slowly in color from gold to green to a pale silver that brightens and dims over the course of hours. This is not the aurora, which is driven by charged particles from the sun. This glow comes from sunlight scattering off the highest reaches of the atmosphere, at altitudes where thin air still catches rays that the Earth's surface has long since lost. In midsummer at extreme latitudes, the sky never fully darkens. A deep blue twilight persists through the hours that elsewhere would be full night. Further toward the poles, the sun does not set at all. It traces a low arc across the horizon, casting long shadows that rotate slowly around objects rather than lengthening, and then disappearing as they do at lower latitudes. The quality of this unending light is different from ordinary daylight, softer and more golden, arriving at an angle that makes everything it touches look slightly unreal. The atmosphere carries an electrical charge that builds and shifts throughout summer in ways that winter rarely produces. As the sun heats the ground, columns of warm air rise rapidly through cooler air above them. These convective currents carry water vapor upward, where it cools and condenses into clouds. Inside a developing storm cloud, the updrafts are powerful enough to carry ice crystals and water droplets upward at speeds that exceed the ability of gravity to pull them back down. As these particles collide in turbulent air, they exchange electrical charge. Smaller, lighter ice crystals tend to acquire a positive charge and get carried to the tops of clouds by updrafts. Heavier particles fall toward the base of the cloud and carry negative charge with them. Over the course of tens of minutes, the top of the cloud becomes strongly positive and the base becomes strongly negative. The ground below, responding to the charge overhead, develops its own induced positive region. When the electrical difference between cloud and ground becomes large enough, a conductive channel of ionized air forms suddenly, bridging the gap in a fraction of a second. The return stroke, the flash we see, carries an enormous current through that channel and heats the surrounding air to temperatures 5 times hotter than the surface of the sun, all in a space narrower than a human thumb. The way that summer storms die is as interesting as the way they form. A thunderstorm requires a continuous supply of warm, moist air rising into its core to maintain the updrafts that sustain the cloud tower and its electrical activity. As a storm matures, its own downdraft, the column of cold air and rain that descends from the cloud base, spreads out across the surface beneath the storm. This cold air undercuts the warm, moist air that was feeding the storm, cutting off the supply of fuel. The updraft weakens. The cloud tower begins to lose its sharp cauliflower top and spreads into an anvil shape as the ice crystals at the summit drift outward with the upper-level winds. The electrical activity decreases. The rain continues for a while as the remaining moisture falls, and then it too diminishes. The whole cycle from the first sign of cumulus development to the final dissipation of the anvil cloud can take anywhere from 30 minutes to several hours depending on the atmospheric conditions. By the time the last traces of cloud are gone, the air that remains is cooler, cleaner, and lower in humidity than the air that existed before the storm. The storm has processed a large volume of warm, moist summer air and returned it to the surface transformed. The freshness that follows a summer thunderstorm is the atmospheric consequence of this transformation. Summer humidity changes not just how the air feels, but how it behaves as a chemical medium. Water vapor is a highly effective absorber of certain types of radiation. When the air is saturated with moisture, Infrared energy released by the warm ground is captured by water molecules before it can escape into space. This trapping of outgoing heat means that humid summer nights cool much more slowly than dry ones. The air above holds warmth like a soft blanket wrapped around the landscape. In desert regions where summer air remains dry, temperatures can drop dramatically after sunset as heat escapes freely upward. In humid coastal or tropical zones, night brings only marginal relief because the moisture-laden air prevents that escape. The water vapor also acts as a solvent in the atmosphere, dissolving gases and particles that would otherwise remain airborne, and enabling chemical reactions that cannot occur in dry air. The particular smell of summer air, that thick organic heaviness that arrives on still afternoons, is partly the smell of these reactions, of volatile compounds released by vegetation dissolving into humid air and undergoing slow transformation before reaching the nose. The length of summer days has measurable effects on the electrical behavior of the upper atmosphere. During long summer days, ultraviolet radiation from the sun strips electrons from gas molecules in the ionosphere, a layer of atmosphere beginning roughly 60 kilometers above the surface. The more hours of sunlight, the more ionization occurs, and the more electrically conductive the ionosphere becomes. This seasonal change alters how radio waves behave. Certain frequencies that pass through the ionosphere easily in winter are reflected back toward the Earth in summer, bouncing between the ionosphere and the ground and traveling great distances. Other frequencies that would have bounced in winter now pass straight through and escape into space. Shortwave radio operators have known for generations that summer propagation behaves differently from winter propagation, and that signals which are reliable in cold months may fade or shift unpredictably in warm ones. The reason is this electrical transformation of the upper atmosphere, driven by the simple fact of extra hours of sunlight. The sky overhead is not passive. It responds to summer by becoming a different kind of electromagnetic environment. Summer transforms the chemistry of air near forests and grasslands in ways that have only recently been fully understood. Trees under heat and light stress release enormous quantities of volatile organic compounds through their leaves. These compounds, which include isoprene and a wide family of terpenes, are the source of the particular scent of pine forests, eucalyptus stands, and warm meadows in summer. But their role goes far beyond scent. Once released into the atmosphere, these compounds react with ozone and with nitrogen oxides from vehicle and industrial emissions. The reactions produce secondary aerosol particles, tiny clusters of molecules that are large enough to scatter light. In regions with dense forests and significant vehicle traffic, these aerosols can build up into a visible haze that hangs over the landscape on hot afternoons. The blue haze that historically gave the Blue Ridge Mountains their name comes partly from this source. The trees are not simply passive recipients of summer heat. They are chemically active, releasing compounds that alter the optical and chemical properties of the atmosphere above them. High-pressure systems that dominate summer weather in many regions create conditions where the atmosphere itself acts as a lid on the landscape. When a dome of high pressure settles over an area, it causes air to slowly sink from above. Sinking air warms as it compresses, and warm air resists forming clouds. The sky remains clear, allowing full solar radiation to reach the surface for day after day. The ground heats, the air near the surface heats, and because the sinking air above prevents vertical mixing, the heat accumulates without escape. Humidity builds as evaporation continues, but moisture cannot rise freely to form clouds. Cities under such systems can experience temperatures significantly higher than surrounding rural areas because their concrete and asphalt surfaces absorb and retain more heat. The air above cities becomes a reservoir of trapped warmth that grows hotter with each successive day of high pressure. When these systems finally break down and storms arrive, the contrast between the accumulated heat and the cooler air brought by the storm can produce intense and rapid weather changes. The angle at which sunlight strikes different surfaces in summer determines the temperature of the landscape with remarkable precision. A south-facing slope in summer receives light that strikes nearly perpendicular to the surface, concentrating the sun's energy into a smaller area and producing intense heating. A north-facing slope on the same hillside receives light at a much shallower angle, spreading the same energy over a larger area and remaining significantly cooler. The difference in temperature between these two slopes can be equivalent to the difference between two entirely different climate zones. The plant communities on each slope reflect this. Drought-tolerant species thrive on the south face, while moisture-loving species survive on the north. The aspect of a slope, the direction it faces, becomes one of the most powerful factors determining local summer conditions, more important in many places than elevation or latitude. Farmers, foresters, and gardeners have understood this intuitively for centuries, but the physics is elegant. The same sunlight produces entirely different environments, depending on nothing more than the geometry of the terrain. Summer air contains a higher concentration of biological material than air in any other season. Pollen from grasses, trees, and flowering plants reaches its seasonal peak in early summer in most temperate regions. Fungal spores rise from the ground and from decomposing matter. Tiny fragments of leaves, insect wings, and animal dander drift on warm updrafts. Bacteria that inhabit the surface of soil and vegetation become airborne when disturbed by wind or rain. This biological aerosol is not merely a nuisance for people with allergies. It plays an active role in weather formation. Many of these particles are highly effective cloud condensation nuclei, surfaces onto which water vapor can condense to form cloud droplets. Clouds that form around biological particles may behave differently from clouds that form around mineral dust or industrial particles. Some researchers have proposed that forests may influence their own rainfall by releasing particles that promote cloud formation above them, a feedback loop in which the forest effectively seeds the clouds that water it. Summer air is not just a mixture of gases. It is a living medium, dense with biological information. The speed at which heat moves through different materials during summer has consequences that shape everything from urban planning to the behavior of wildlife. Stone, concrete, and metal absorb heat from the sun during the day and release it slowly through the night. A city street paved in dark asphalt can reach temperatures far above air temperature on a summer afternoon, creating a thermal environment hostile to barefoot walking, but also radiating heat upward that contributes to the warmth felt at body height. Soil with high moisture content absorbs less heat because water requires significant energy to warm compared to dry mineral particles. A wet lawn stays cooler than a dry one, even under identical sunshine. Sandy beaches heat rapidly because sand is a poor conductor and heat does not penetrate deeply, concentrating instead in the surface layer. The temperature gradient from the surface of sand to a few centimeters below it on a summer afternoon can be enormous. The same sun creates dramatically different thermal environments depending on what the surface is made of, and how much water it holds. Summer changes the way the ocean's surface exchanges gas with the atmosphere above it. As surface water warms, its capacity to dissolve oxygen and carbon dioxide decreases. Gases that would remain dissolved in cold water are released into the air as temperatures rise. This seasonal outgassing shifts the balance of gases in the marine boundary layer, the thin region of atmosphere directly above the ocean surface. At the same time, increased light and warmer temperatures drive explosive growth in phytoplankton populations, which consume carbon dioxide through photosynthesis and release oxygen. The competition between outgassing driven by warmth and uptake driven by photosynthesis determines whether a patch of summer ocean is a net source or sink of atmospheric carbon at any given moment. Dimethyl sulfide, a gas produced by certain species of marine algae, is released in much larger quantities in summer as algae populations bloom. This gas, once in the atmosphere, reacts to form sulfate particles that serve as cloud condensation nuclei, linking ocean biology directly to cloud formation and potentially to regional climate. Sunlight in summer penetrates the surface of lakes and ponds to depths that change the entire biological character of the water column. Clear water allows light to reach several meters down, driving photosynthesis in layers that would remain in darkness during cloudier seasons. As algae and aquatic plants photosynthesize, they release oxygen into the water during daylight hours. But at night, the same organisms respire, consuming oxygen and releasing carbon dioxide. In shallow productive lakes during long summer nights, oxygen levels near the surface can drop significantly as biological demand exceeds supply. Deeper in the water column, where light never reaches, decomposition of organic matter settles from above consumes oxygen steadily regardless of the season. By midsummer in many temperate lakes, the deep water has become essentially anoxic, a zone where only anaerobic microbes can survive. This stratification of oxygen, light, and temperature divides the lake into distinct ecological zones, each with its own community of organisms adapted to the precise conditions found at that depth. The thermal expansion of air in summer has effects that extend from the microscopic to the planetary. When air is heated, its molecules move faster and push against one another more forcefully, causing the gas to expand and become less dense. This expansion is the engine behind summer's convective weather. Hot air near the ground is less dense than cooler air above and rises buoyantly, carrying heat and moisture upward. As it rises, it expands further, cools, and eventually reaches a level where the moisture it carries condenses into cloud droplets. The energy released when water vapor condenses warms the surrounding air, giving additional buoyancy to the rising column. The result is a self-reinforcing engine that can build a towering thunderstorm from a simple patch of heated ground in the space of a few hours on a summer afternoon. The same physics operates across the entire planet. Differential heating between the equator and poles, between land and sea, between forest and desert, drives the circulation of the atmosphere and creates the patterns of wind and weather that define the summer season. Ozone in the lower atmosphere behaves very differently in summer from how it behaves in the upper atmosphere, where it provides protection from ultraviolet radiation. Near the ground, ozone is a pollutant, formed through a series of chemical reactions that require both sunlight and precursor compounds such as nitrogen oxides and volatile organic compounds. Summer provides the long hours of intense sunlight and the warm temperatures that accelerate these reactions. In urban areas with significant vehicle traffic and industrial emissions, summer afternoons can produce ozone concentrations high enough to irritate the respiratory system and damage vegetation. Plants exposed to elevated ozone show visible damage on their leaves and grow more slowly. Ozone also reacts with other compounds in the air, breaking them down into still other substances that contribute to the chemical complexity of summer haze. The same season that fills the sky with deep blue and golden light also drives a chemical factory in the lower atmosphere, converting the exhaust of human activity into a mixture of compounds that would not exist without the specific conditions of summer. The chemistry of afternoon summer air in a city differs measurably from the chemistry of morning air in the same location. Through the night, emissions from vehicles and industry accumulate in the stable nocturnal air, building concentrations of various compounds near ground level. As the sun rises and heating begins, vertical mixing stirs this accumulated layer upward and disperses it. But by late morning and into the afternoon, a new cycle of photochemical reactions has been running for hours, converting precursor compounds into ozone and other secondary pollutants. The afternoon air carries the products of a full day of sunlight-driven chemistry, while the morning air carries the products of a night of accumulation with little photochemical processing. For people sensitive to air quality, these differences are not abstract. The advice to exercise in the morning rather than the afternoon during summer is partly a recognition of this daily chemical cycle, a recommendation to take advantage of the hours before the photochemical factory of a summer day has run to its afternoon peak. The air itself is telling a story of chemistry driven by sunlight, and the story is different at every hour of the day. The way that moisture moves from the ground into the atmosphere in summer shapes weather across entire continents. When soil is warm and well supplied with water, evaporation rates are high. Vegetation adds to this through transpiration, the process by which plants draw water up through their roots and release it through tiny pores in their leaves. A mature forest on a summer day can release thousands of liters of water vapor per hectare into the air above it. This moisture rises with the heated air, cools and condenses into clouds. The clouds may drift downwind and eventually produce rainfall hundreds of kilometers from where the moisture originally entered the atmosphere. The Amazon rainforest generates so much moisture through this cycle that it creates what researchers call flying rivers, atmospheric rivers of water vapor that carry moisture westward until it rises against the Andes and falls as rain. The forests are not simply living in the climate. They are helping to create it, moving water from the soil into the sky with a persistence and efficiency that shapes rainfall patterns across the continent. Summer air carries information encoded in molecules that most living things can read far more precisely than any instrument humans have built. Volatile chemicals released by plants under stress, by animals marking territory, by flowers advertising their nectar, by decaying matter signaling its transformation. All of these drift through summer air and form a chemical landscape as detailed as any visual or acoustic environment. Many insects navigate by this chemical landscape, following concentration gradients of specific molecules across distances of several kilometers. Predatory insects locate their prey partly by the compounds the prey releases when stressed. Parasitic wasps find caterpillars hidden inside plant tissue by detecting the specific volatile compounds the plant releases in response to being eaten. Pollinators track the scent plumes of flowers downwind, moving against the concentration gradient until they arrive at the source. This chemical communication operates in summer with a richness and complexity that cooler months cannot match, because warm air carries more molecules in vapor form, and because the biological activity that generates these chemical signals reaches its annual peak when temperatures are highest and days are longest. As the last details of that first long summer evening settle quietly into your thoughts, there is nothing left to track, nothing left to follow. The chemistry of the air, the geometry of light, the slow electrical breath of the atmosphere, all of it can soften now into the background. You have traveled far enough for one night. Let the warmth hold you where you are. The ocean's surface in summer develops a layered structure that separates the sea into worlds that barely communicate with each other. As sunlight pours into the upper water, the surface layer absorbs heat and becomes warmer and less dense than the water below. This lighter warm water floats above the cooler, denser deep water without mixing freely. The boundary between these two layers, called the thermocline, can be sharp enough that a diver passing through it feels the temperature change in an instant, like crossing from one room into another. Above the thermocline, summer sunlight supports explosive growth of phytoplankton and the animal communities that feed on them. Below it, the water remains cold and dark, cut off from the warmth and light of summer as completely as if the season did not exist. Nutrients that sink from the surface layer into the deep water cannot easily return to the light zone because the density difference resists vertical mixing. As summer progresses, the surface layer can become nutrient depleted even as the water below remains rich. The thermocline is an invisible wall inside the ocean that summer builds and maintains for months. The ocean produces light of its own in summer through a process that has no mechanical part and requires no energy source other than a chemical reaction inside a living cell. Bioluminescence occurs when certain marine organisms oxidize a compound called luciferin in the presence of an enzyme, releasing energy as visible light instead of heat. Dinoflagellates, single-celled organisms that bloom in enormous concentrations during warm summer months, are among the most spectacular producers of this light. When disturbed by a wave, a swimming animal, or the hull of a passing boat, these organisms flash blue-green light that can make entire bays glow on summer nights. The light is not an accidental byproduct of their chemistry. In many cases, it appears to serve functions such as startling predators or attracting larger predators to consume the animals eating the dinoflagellates. On beaches where bioluminescent plankton are abundant, the foam at the waterline glows with each wave, and footprints left in wet sand at the ocean's edge pulse faintly with blue light for several seconds before fading. This phenomenon peaks in summer because the warm water and long days accelerate the growth of the populations responsible for it. Evaporation from the ocean's surface in summer moves an almost incomprehensible quantity of water into the atmosphere each day. The process is invisible and continuous, occurring molecule by molecule as water at the surface acquires enough energy from sunlight and warm air to escape into the gas phase. Over the tropical oceans in summer, evaporation rates are so high that the atmosphere above the sea becomes enormously laden with moisture. This moisture is the fuel of tropical weather systems. When it condenses inside a developing storm, it releases the latent heat that was stored when the water evaporated, and this heat drives the upward motion that organizes the storm. A mature tropical cyclone extracts energy from warm ocean water through evaporation with an efficiency that has no parallel in any engineered power system. The heat energy contained in a single day's evaporation from a patch of warm tropical ocean is equivalent to many thousands of nuclear power plant outputs. Summer over the tropical ocean is an enormous and continuous engine, converting solar energy into atmospheric motion through the mechanism of evaporation and condensation. The surface tension of water changes measurably with temperature, and this shift has consequences that reach from the microscopic to the ecological. In summer, warmer water has lower surface tension than cold water. The thin elastic skin that allows small insects to walk on water becomes slightly less rigid, changing the conditions under which surface-dwelling creatures can operate. At the same time, the reduced surface tension affects how bubbles form and break at the ocean surface. When a wave breaks and traps air beneath it, thousands of tiny bubbles form and rise. As they burst, they eject tiny droplets of seawater into the air above, carrying dissolved salts, organic molecules, and microorganisms with them. These sea spray droplets become airborne particles that can travel far inland on summer winds, delivering the chemical signature of the ocean to places far from the coast. The concentration of these particles in coastal summer air is high enough that the taste and smell of the sea can be detected kilometers from shore. The ocean is constantly exhaling part of itself into the atmosphere, and summer's warmer temperatures accelerate this exhalation. Ocean currents shift their character in summer in ways that reach far beyond the water itself. Along the western coasts of continents, prevailing summer winds push surface water away from shore. To replace this departing water, cold water wells up from the deep. This upwelling brings nutrients from the depths into the sunlit zone and triggers enormous blooms of marine life. The cold upwelled water also chills the air above the coast, creating fog that rolls inland on summer mornings. Coastal cities in upwelling zones can be significantly cooler than cities at the same latitude far from the coast, even in the height of summer. The cold water moderates summer temperatures, keeps the air moist, and shapes the entire ecology of the coastal zone. Farther offshore, warm currents bring their own weather. The Gulf Stream carries warm water northward along the eastern coast of North America with a volume of flow that dwarfs all the rivers on Earth combined. Its warmth moderates winters in northwestern Europe. In summer, the contrast between the warm current and cooler surrounding water generates persistent fog banks and creates conditions that influence storm tracks across the North Atlantic. Lakes in summer undergo a transformation as profound as the one that happens in winter, but in the opposite direction. Warming surface water becomes less dense and floats on top of colder water below. The two layers stop mixing because the density difference resists the turbulent exchange that characterizes cooler seasons. Nutrients that settle from the surface into the deep water cannot return to fuel more growth at the top. Oxygen produced by photosynthesis near the surface cannot reach the dark depths where decomposition consumes it. The lake becomes a stratified system with distinct zones, each chemically different from its neighbors, separated by only a few meters of water. Fish species sort themselves by the temperature and oxygen content of each layer, concentrating wherever the conditions match their particular requirements. In very productive lakes, the surface layer can develop dense blooms of cyanobacteria that shade the water below, preventing photosynthesis at deeper levels and altering the entire chemistry of the lake. These blooms are amplified by summer heat and long days and can persist for weeks, changing the color of the water to green or blue-green and releasing compounds that are toxic to animals that drink or swim in the affected water. Rainfall in summer arrives differently than in other seasons and changes the land it falls on in ways specific to that time of year. Summer rain often comes in intense short bursts from convective storms rather than in the long, steady precipitation of frontal systems, more common in cooler months. A convective storm can deliver several centimeters of rain in an hour to a small area, while leaving an adjacent area completely dry. The intensity of this rain matters enormously for what happens when it reaches the ground. Heavy rain falling faster than the soil can absorb it runs off the surface, carrying topsoil and organic matter with it. In summer, when the ground is often baked hard by weeks of heat, and the organic material in the soil has dried and lost its water-retaining structure, runoff is especially rapid. The water that does enter the soil moves differently than in other seasons because warm soil bacteria process organic compounds quickly, changing the chemistry of the water as it percolates downward. The smell of rain on dry summer earth, that sharp, pleasant scent called petrichor, comes from oils released by drought-stressed plants and from a compound called geosmin produced by soil bacteria that are suddenly reactivated by moisture after a dry period. The humidity of summer air changes the behavior of sound in ways beyond the simple effect of temperature. Moist air is actually less dense than dry air at the same temperature and pressure, a fact that seems counterintuitive, but follows from the molecular weights of water vapor and the nitrogen and oxygen it partially displaces. Sound travels slightly faster in humid air than in dry air, but more significantly, humid air absorbs certain frequencies of sound more efficiently than dry air does. High-pitched sounds are absorbed more strongly, meaning that in humid summer air, distant sounds lose their high-frequency components faster than in dry air. A voice heard at a distance in humid summer air sounds slightly different from the same voice heard at the same distance in dry winter air, lower, slightly muffled, with less of the sharp clarity that dry cold air preserves. This differential absorption by humidity is one of the reasons that summer sounds have a characteristic quality, a soft thickness that is partly meteorological rather than purely a product of the sounds themselves. The persistence of summer warmth into the night in humid regions is a physical phenomenon with a precise mechanism that connects the chemistry of water to the experience of lying awake in heat that will not break. During the day, vast quantities of water evaporate from vegetation, soil, and open water surfaces, entering the air as vapor. This vapor carries with it the latent heat that was required to accomplish the phase change from liquid to gas. In the evening, as the air cools, some of this vapor begins to condense back into liquid, releasing the stored latent heat into the surrounding air. In a dry climate, the air cools rapidly at night because there is little water vapor to release heat through condensation. In a humid summer climate, the water vapor in the air acts as a heat reservoir that releases its stored energy as the night progresses, slowing the rate of cooling and maintaining temperatures that deny relief to anyone trying to sleep without artificial cooling. The mugginess of summer nights in humid regions is not simply uncomfortable. It is the physical consequence of an enormous amount of energy stored in water vapor throughout the day and slowly released back into the air as evening condensation occurs. The night is not failing to cool. It is cooling as fast as the physics allow, which in a water-saturated atmosphere is not fast enough for comfortable sleep. The chemistry of water changes when it warms, and these changes propagate through entire food webs. Cold water holds more dissolved oxygen than warm water. As lake and river temperatures rise through summer, the available oxygen decreases, forcing aquatic animals that depend on high oxygen concentrations to move to cooler, deeper water, or to use behavioral strategies to compensate. Fish that evolved in cold mountain streams may become physiologically stressed in summer when temperatures in lowland rivers rise toward the upper limits of their tolerance. The metabolic rate of fish also increases with temperature, meaning they need to eat more even as the energetic cost of extracting oxygen from warm, depleted water increases. The same warming that stresses cold water fish can benefit warm water species, accelerating their growth and reproduction. Summer creates a seasonal reshuffling of competitive advantage across the spectrum of aquatic life, with warm-adapted species expanding their activity and cold-adapted species retreating to the narrowing zones of cold water that remain available. Water moving through rivers in summer carries a different chemical signature than river water in other seasons. The combination of low flow, warm temperatures, high biological activity, and intense sunlight creates conditions in which river chemistry changes rapidly over short distances. Photosynthesis by aquatic plants and algae raises the pH of river water during daylight hours as carbon dioxide is consumed and oxygen is produced. At night, respiration reverses this, consuming oxygen and releasing carbon dioxide, lowering pH in productive rivers during summer. This daily cycle of pH change can be dramatic enough to stress fish. Downstream from cities and farms, nutrients carried in the water fuel algal growth that can strip oxygen from slow-moving summer water. Where groundwater seeps into rivers through gravelly beds, it emerges cold and clear, creating thermal refuges where cold water fish concentrate. The river is not a uniform body of water, but a mosaic of chemical and thermal environments that summer makes more varied and more extreme than any other season. The behavior of waves on the ocean surface in summer reflects the pattern of winds that drive them, and those winds in summer follow patterns shaped by the differential heating of land and sea. As land heats more quickly than the ocean during the day, a pressure difference develops that drives a sea breeze from water toward land during afternoon hours, then reverses at night as the land cools faster than the water and air flows back offshore. Along coastlines where these breezes are predictable, the rhythm of wind direction through the day shapes the wave pattern on the water. Morning seas are often calmer because the nighttime offshore breeze has been relatively gentle. Afternoon seas become rougher as the sea breeze strengthens. Sailors and surfers who work with these patterns develop an intimate knowledge of the local timing that is essentially a knowledge of the physics of heat exchange between the land and the sea. In some coastal regions, the daily heating of interior land masses creates such strong pressure gradients that the sea breeze reaches gale force by afternoon, a thermally driven wind that operates reliably day after day through the summer months. Wetlands in summer release gases from below their waterlogged surfaces that would remain trapped in cooler seasons. Decomposing organic matter buried beneath the water and waterlogged soil is broken down by anaerobic bacteria, microbes that operate without oxygen. These bacteria produce methane as a byproduct of their metabolism. In summer, the combination of higher temperatures, which accelerate bacterial activity, and the growth of aquatic plants, which transport gases between the sediment and the atmosphere through internal air channels, causes wetlands to exhale large quantities of methane into the air above. Some of this methane bubbles up visibly through the water in a process called ebullition, releasing clusters of bubbles that pop at the surface with small but audible sounds on quiet summer mornings. The methane released from wetlands and other warm, wet environments is a significant component of the atmospheric budget of this gas. Summer warmth is one of the primary drivers of seasonal variation in the rate of this release. Cold months slow the bacteria. Warm months wake them. Coastal estuaries where rivers meet the sea undergo some of their most dramatic transformations in summer. As river flow often decreases during dry summer months, the penetration of salt water upstream increases. The zone where fresh and salt water mix moves far upriver from its winter position. This shift exposes areas of the estuary to salinities they do not experience in other seasons, stressing or killing freshwater organisms that live there, and creating opportunities for salt-tolerant species to expand their range. At the mixing zone itself, the collision of water masses with different densities and chemical compositions creates a chemically active region where dissolved materials flocculate and settle, where nutrients are transformed from one chemical form to another, and where biological productivity can be very high. Summer stratification also affects estuaries. The lighter fresh river water tends to float over the denser salt water, creating a layered system in which the upper layer flows toward the sea and the lower layer flows upstream. Nutrients, sediments, and organisms are sorted and transported by this two-layer circulation in ways that shape the ecology of the estuary throughout the season. The way that light penetrates water changes the life that can exist in any given layer. Pure water absorbs light of different colors at different rates. Red wavelengths are absorbed within the first few meters. Orange and yellow follow. Green and blue penetrate deepest, which is why the deep ocean appears blue to a diver looking upward toward the surface. In summer, when sunlight is intense and the angle of incidence is steep, more light reaches deeper layers than in winter. A coral reef in summer is a brighter environment than the same reef in winter, with photosynthetic organisms receiving more energy and growing more rapidly. But summer also brings warm surface water that in some regions causes coral bleaching, a stress response in which corals expel the photosynthetic algae that live inside them and provide much of their energy. The same season that delivers the most light delivers the most warmth, and the balance between these two effects determines whether a reef thrives or struggles. Summer is simultaneously the season of maximum photosynthetic opportunity and maximum thermal stress for the organisms that build the largest biological structures on Earth. Fresh water floating at the surface of the ocean after heavy summer rains creates thin lenses of low salinity water that behave differently from the sea beneath them. The boundary between the fresh surface layer and the saltwater below can be sharp enough to reflect sound, creating an acoustic mirror that disrupts the communication of marine mammals. Dolphins and whales use sound to navigate and find prey, and a lens of fresh surface water can trap their signals in the upper layer or reflect them in unexpected directions. At the same time, organisms that prefer lower salinity can colonize these surface lenses, creating temporary ecological communities that drift with the wind and current before gradually mixing into the surrounding sea. The fresh water also changes the temperature of the surface layer because it does not transfer heat downward into the salt water as efficiently. A patch of surface freshwater under a summer sun can become considerably warmer than the ocean around it, creating a thermal anomaly visible from satellites as a bright patch of elevated sea surface temperature. Underwater light in summer creates conditions for a phenomenon that few people who have not dived in clear tropical water have ever witnessed. When sunlight enters shallow, clear water over a sandy or reflective bottom, the waves at the surface act as a network of moving lenses, each focusing and defocusing the light below. The result is a constantly shifting pattern of bright lines and rings on the seafloor, moving with the motion of the waves. These caustic patterns, named after the mathematical curves they trace, can be extraordinarily beautiful. They are also a physical record of the shape and motion of every wave passing overhead, written in light on the bottom. In deeper water, multiple layers of refraction from different wave systems can create complex overlapping patterns. For some animals living on the seafloor, these patterns of moving light may provide information about wave conditions at the surface, though how much attention any particular species pays to this shifting light display is not fully understood. Summer, with its calmer seas and clearer water in many regions, provides the conditions most favorable for these patterns to develop and persist for the hours needed to observe them. The chemistry of seawater changes with the season in ways that influence everything living in it. Dissolved oxygen, carbon dioxide, and nutrients fluctuate predictably through the year. But summer also brings changes in the concentrations of trace metals, vitamins, and organic compounds that are harder to measure but equally important to marine life. Iron, which is often the limiting nutrient for phytoplankton growth in vast stretches of the open ocean, can arrive in summer from unexpected sources. Dust blown from arid land masses carries iron particles that dissolve when they settle on the sea surface. Summer winds over certain deserts drive large dust plumes out to sea, fertilizing patches of ocean that would otherwise be biological deserts. When this iron arrives, it triggers phytoplankton blooms within days. The blooms consume carbon dioxide, alter the reflectivity of the sea surface, and produce gases that interact with the atmosphere. A cloud of dust settling on a summer sea sets off a chain of biological and chemical events that can alter the weather above it. The ocean and the atmosphere are not separate systems. They are partners in a seasonal conversation. River deltas at the mouths of large rivers are built and rebuilt in summer by the sediment carried downstream during high flow periods. As rivers widen and slow when they reach the sea, they drop the load of silt, sand, and organic material they have been carrying for hundreds or thousands of kilometers. This deposition builds the delta outward into the sea. In summer, the organic content of this sediment is high because rivers carry material from productive land ecosystems. When this organic material reaches the anaerobic sediment of the delta floor, it is decomposed by bacteria that consume oxygen, creating dead zones in the water above. The Mississippi River Delta generates one of the largest seasonal dead zones in the world each summer, fueled by nutrients from agricultural land far upstream that fertilize algal blooms. And when the algae die and sink, their decomposition strips oxygen from the water. This dead zone fluctuates in size through the summer season depending on river flow, wind mixing, and the timing and intensity of algal blooms. It is a direct consequence of the way that summer river chemistry meets summer ocean stratification. Water underground behaves differently in summer than in other seasons in ways that affect surface ecosystems in unexpected ways. Groundwater temperatures remain relatively stable compared to surface temperatures, because soil insulates the water from daily and seasonal extremes. But summer heat slowly penetrates downward through months of warming, and by late summer, even groundwater at moderate depth is slightly warmer than it was in spring. Where groundwater discharges into streams, it arrives at a temperature that has been slowly integrating months of surface conditions. In early summer, groundwater-fed streams may be unusually cold, providing critical refuges for temperature-sensitive fish. By late summer, this advantage has diminished. The lag between surface heating and groundwater warming means that groundwater-fed systems respond to summer heat on a timeline of weeks to months rather than days. Understanding this lag is essential for managing water systems under conditions where summer heat waves are becoming longer and more intense. The underground reservoir does not immediately reflect the crisis at the surface. It announces it, slowly, weeks later. Soil in summer becomes one of the most biologically active environments on the planet. Warmth accelerates the metabolism of every organism living in the ground, from bacteria too small to see without a microscope to the fungal networks that thread through the soil between plant roots. Decomposition rates increase sharply with temperature. Dead leaves, fallen branches, insect bodies, and animal waste that accumulated through cooler months are broken down rapidly when the soil warms. The carbon locked inside this organic material is converted to carbon dioxide and released into the air above, or transformed into simpler compounds that dissolve in soil water and become available to plant roots. The smell that rises from warm, moist summer soil, that rich, dark earthen scent, is partly the smell of this accelerated decomposition, of billions of microbes metabolizing at their seasonal peak. In a single teaspoon of healthy summer soil, the number of bacteria can exceed the number of people who have ever lived on Earth. These organisms are not simply passive decomposers. They transform nutrients from one chemical form to another, make minerals accessible to plants, produce compounds that influence plant growth and immunity, and drive the invisible engine that keeps surface ecosystems running. Plants move water from the ground to the air in summer at rates that would seem extraordinary if the process were visible. A single large oak tree can pull hundreds of liters of water upward through its trunk and release it through its leaves on a hot summer day. This process, called transpiration, is driven by the difference in water concentration between the inside of a leaf and the dry summer air outside. Water molecules evaporate from the wet surfaces inside the leaf and escape through tiny pores called stomata. As they leave, they pull more water molecules behind them through surface tension, creating a column of water under tension that extends all the way down through the trunk and into the root system. This column is under negative pressure, meaning the water is being pulled rather than pushed. The forces involved are large enough to draw water upward against gravity to the tops of the tallest trees on Earth. In summer, when transpiration rates are highest, this hydraulic system operates at its limits. During prolonged drought, the tension in the water columns can become so great that air bubbles form inside the conducting tissue, breaking the column and causing branches to die. The network of fungal threads that connects the roots of trees in a summer forest carries materials in both directions simultaneously. Sugars produced by photosynthesis in the leaves of trees flow downward to the roots and then into the fungal network, feeding fungi that cannot photosynthesize. In exchange, the fungi, whose threads extend far beyond what the roots themselves could reach, absorb water and mineral nutrients from the surrounding soil and pass them into the roots. This exchange has been operating for hundreds of millions of years, and is so fundamental that most land plants cannot grow normally without it. In summer, when photosynthesis is running at full speed and demand for water and nutrients is highest, the traffic through this underground network is intense. Carbon flows outward from productive trees to neighboring trees that may be shaded or stressed. Nitrogen and phosphorus flow inward from the far reaches of the fungal network. Scientists studying these exchanges have found that older, larger trees in a forest contribute more carbon to the network than younger ones, effectively subsidizing the growth of seedlings in the deep shade of the forest floor. Summer is the season when this subterranean economy operates at its most vigorous. Flowers that open at night in summer are solving a specific problem created by the abundance of daytime pollinators. During the day, competition for pollinators among flowering plants is intense. Bees, butterflies, and other daytime insects visit enormous numbers of flowers, sometimes transferring pollen between the wrong species or consuming nectar without completing pollination. Plants that flower at night avoid this competition entirely. Their pollinators are moths, bats, and night-flying beetles, animals that are active only after dark and that visit far fewer flowers in a given night than daytime pollinators do. To attract these nocturnal visitors, night-blooming flowers produce scents rather than relying primarily on visual signals. These scents are often heavy, sweet, and complex, detectable from distances of many meters in the still summer night air. The white or pale yellow color common in night-blooming flowers reflects moonlight and starlight, making them faintly visible in darkness. The timing of scent production is often precisely controlled, with peak emission occurring during the hours when the relevant pollinator is most active. Summer nights carry the perfume of these flowers as a chemical announcement made to an audience of navigating animals. Grasses growing in open summer fields are among the most efficient photosynthesizers of any plant group, using a biochemical pathway that allows them to capture carbon dioxide from the air more effectively than most other plants under conditions of high temperature and intense sunlight. This pathway, called C4 photosynthesis, involves a preliminary step that concentrates carbon dioxide before it enters the primary reactions of photosynthesis, reducing the energy wasted when the photosynthetic enzymes mistakenly process oxygen instead. At the high temperatures and light intensities of summer, C4 plants have a significant advantage over plants using the more common C3 pathway. The grasslands that dominate the interiors of continents are composed predominantly of C4 species that evolved under the warm, dry, high-light conditions of the growing season. Their efficiency allows them to grow rapidly and produce large amounts of biomass, even in conditions that stress other plants. The waving surface of a summer grass field converts sunlight to organic matter with a consistency that shapes the ecology of everything that depends on those grasses, from the insects that feed on them to the large herbivores whose migrations track the flush of summer growth. The chemical conversation between plants and the insects that attack them runs continuously through summer and involves compounds of remarkable complexity and specificity. When a caterpillar begins chewing on a leaf, sensors in the damaged tissue detect specific compounds released from the insect's saliva. Within minutes, the plant begins activating genes that produce defensive chemicals. Some of these chemicals make the leaf tissue less digestible. Others are toxic to the insect. Still others are volatile and escape into the air, where they travel downwind to neighboring plants of the same species. which respond by activating their own defenses before any insect has reached them. Some of these airborne distress signals are specific enough that they attract the predators and parasites of the insects causing the damage. A plant being eaten by aphids releases a blend of volatiles that draws parasitic wasps to the scene, wasps that lay their eggs inside the aphids, killing them from within. These interactions have been refined over millions of years of coevolution between plants and their attackers, and they run continuously through summer, invisible to anyone passing through a field or forest, without the tools to detect them. Soil temperatures in summer vary dramatically over short distances in ways that create entirely different microhabitats within centimeters of each other. The surface of bare, dark soil in direct sunlight can reach temperatures lethal to most organisms, while the soil a few centimeters below the surface may be 20 or 30 degrees cooler. The shaded side of a stone can be significantly cooler than the exposed side of the same stone. The north and south sides of a small hill accumulate heat at different rates through the day. These microthermal variations structure the distribution of soil organisms, insects, and small plants at a scale too fine to appear on any map. Beetles that prefer warm, dry conditions congregate on south-facing slopes and bare patches. Moisture-loving springtails concentrate under logs and stones. Seeds that require specific temperature ranges to germinate find the narrow zones where conditions match their requirements. The landscape of a summer field, viewed from the perspective of a millimeter-scale organism, is a mosaic of extreme environments as varied as any large-scale geography. Summer amplifies these variations by pushing temperatures to extremes that other seasons moderate. The soil beneath a summer city behaves differently from soil beneath a summer field or forest, and these differences extend deep enough to affect everything growing in it and everything built on top of it. Urban soil is typically compacted by foot traffic and vehicle weight, reducing the spaces between particles where water, air, and roots would normally move. This compaction slows the drainage of rainwater and reduces the oxygen available to roots and soil organisms. The sealed surfaces of streets and buildings prevent rainfall from entering the ground at all over large areas, routing it instead into drainage systems that carry it away from the city. The soil that does receive water in urban parks and gardens receives it infrequently and often in large, sudden inputs rather than in the gentle, continuous percolation that natural surfaces provide. The temperature of urban soil is elevated by the heat island effect, accelerating microbial activity, but also increasing the rate of water loss through evaporation. Trees planted in urban soil face all of these challenges simultaneously, which is why urban trees often live shorter lives and grow more slowly than trees in natural settings, despite receiving more attention and care. The ground beneath a summer city is a stressed and altered medium, shaped by the weight and heat and impermeability of everything built above it. Tree rings record each summer's growth as a layer of wood that can be read decades and centuries later. In spring and early summer, trees produce large, thin-walled cells that form pale, low-density wood. As summer progresses and growth slows, the cells produced are smaller and thicker-walled, forming the dark, dense latewood that marks the end of one season's growth. The width and density of each annual ring reflects the conditions of that particular summer. A wide, dense ring indicates a long, warm, well-watered growing season. A narrow ring indicates drought, cold, or other stress. The ring records not just the average conditions of the summer, but details of timing. A narrow, pale band in the middle of a wide ring might indicate a brief drought in midsummer that slowed growth temporarily before rain resumed. By reading the rings of many trees from the same region and cross-dating them to create long chronologies, researchers can reconstruct summer temperatures and rainfall patterns for centuries or millennia before any written weather records were kept. A cross-section of a single old tree trunk is a summer archive. Each year's ring a compressed record of what the season brought. Dew that forms on grass and leaves in summer nights carries out a process that matters more to certain ecosystems than rainfall does. As surfaces cool by radiating heat into the clear night sky, they reach the dew point, the temperature at which the air immediately above them becomes saturated with water vapor. Moisture condenses directly onto the cool surface, forming droplets that accumulate through the night. By dawn, a grass field can be carrying a significant quantity of water in the form of dew, enough to wet clothing thoroughly. For small insects and spiders, these droplets are a critical source of drinking water during dry summer periods when rainfall is infrequent. For plants in coastal and fog-prone regions, dew and fog drip can contribute a significant fraction of total annual water input. Some desert plants have evolved structures specifically to collect dew, channeling droplets toward their roots. The water that forms as dew was already in the air. It has not fallen from a cloud. It has simply crossed the phase boundary from vapor to liquid because the surface below it became cool enough. Summer nights, clear and radiatively cooling, are the most productive dew-forming nights of the year in many regions. The carbon stored in the bodies of summer insects represents one of the most rapidly cycling pools of organic material in terrestrial ecosystems. Insects complete their life cycles faster than almost any other animal group. A generation of aphids can pass through multiple complete cycles of birth, growth, reproduction, and death within a single summer month. The organic material that flows through insect populations, consumed from plants and excreted, consumed by predators and excreted again, moves through the food web at a pace that slow-growing vertebrates cannot match. This rapid cycling means that summer insect populations are a highly dynamic component of ecosystem carbon and nutrient flows. A sudden crash in an insect population, caused by pesticide application, disease, or weather, immediately affects everything that feeds on those insects and everything that the insects were consuming. The insects are not ornamental inhabitants of summer ecosystems. They are the primary mechanism by which plant biomass is converted into animal biomass and made available to larger creatures. Without the insect layer in summer food webs, the productivity of the season could not be transferred upward to birds, bats, fish, and the hundreds of other species that depend on insect abundance. The way that heat moves through living plant tissue determines how plants survive summer and how they influence the microclimate around them. Leaves are thin structures with a large surface area relative to their volume, which makes them effective exchangers of heat with the surrounding air. A leaf in full sun absorbs more energy than it uses for photosynthesis, and more than its physical mass can hold without overheating. It disposes of this excess heat primarily through transpiration, the evaporation of water from its surface. Evaporation is a highly effective cooling process. The energy required to convert liquid water to water vapor is substantial, and this energy is drawn from the leaf surface as heat. A well-watered leaf on a hot summer day can maintain a temperature close to air temperature or even slightly below it, despite absorbing intense solar radiation. A drought-stressed leaf that has closed its stomata to conserve water cannot cool itself through evaporation and may reach temperatures that damage its proteins. The temperature difference between a healthy transpiring leaf and a drought-stressed leaf on the same branch on a summer afternoon can be several degrees, a difference large enough to alter the rate of every chemical reaction inside the tissue. Decomposition in summer forest floors creates heat that can be measured above the accumulated dead leaves and woody debris. Bacteria and fungi breaking down organic matter release the chemical energy stored in it. Most of this energy is dispersed as heat. In a thick layer of moist leaf litter during a warm, humid summer, the microbial activity is intense enough to raise the temperature of the litter noticeably above air temperature. Compost piles, which are essentially concentrated versions of the forest floor decomposition process, can reach temperatures high enough to pasteurize organic material. In natural settings, the effect is less extreme, but still significant. The thermal environment of the forest floor in summer is partly biological in origin. Organisms decomposing the debris of previous seasons are warming the environment they inhabit. This warmth accelerates their own metabolism further, creating a feedback that drives summer decomposition rates to their annual peak. By autumn, when temperatures begin to fall and fresh leaf litter has not yet fully broken down, the biological heat generation slows and the decomposition rate drops with it. Roots growing through summer soil follow gradients of moisture, nutrients, and oxygen that change day by day as conditions shift. A root tip growing toward a pocket of moist soil does not randomly explore. It responds to chemical and moisture signals in the surrounding medium, extending preferentially in directions that offer better resource conditions. In summer, as the surface soil dries during dry spells, roots that were previously concentrated near the surface begin extending deeper, following the retreating moisture front downward. When rain arrives and re-wets the surface layers, roots near the surface proliferate rapidly to capture the suddenly available water before it drains away. The root system of a single large tree is not a fixed structure. It is a dynamic network that is constantly growing at its tips, dying at its older ends, and redirecting its exploration based on current conditions. In summer, when the pace of both growth and resource depletion is fastest, this dynamic exploration is at its most active. The roots of neighboring trees intermingle below the surface, sometimes fusing where they contact each other, creating physical connections between individuals that have been standing meters apart for decades. Summer grass fires follow paths determined by the distribution of dry fuel, terrain, and wind, and the physics of their propagation has shaped the ecology of grasslands over millions of years. Dry summer grass ignites readily, and once burning, the fire moves with the wind, heating the unburned grass ahead of it until the volatile compounds inside the dry tissue reach their ignition temperature. The fire front advances not just through direct contact, but through radiant heat and the short-range transport of burning embers. Steep terrain accelerates fire because flames lean uphill and preheat the fuel above them. The same fire that moves slowly along flat ground can race up a slope. In regions with a long evolutionary history of fire, the plant community has adapted. Grasses regrow from underground root systems that survive the passage of the fire. Some tree species have thick bark that insulates the living tissue beneath. Others have seeds that germinate preferentially after fire, responding to the heat, the smoke, or the sudden availability of light and nutrients that a burned landscape offers. Summer fires are destructive events from the perspective of any individual plant, but they are part of the ecological rhythm that maintains grasslands as grasslands rather than allowing them to be replaced by shrubs and trees. Photosynthesis in summer reaches its physical limits on the hottest and brightest days in ways that most people looking at a flourishing green landscape would not suspect. The enzymes responsible for fixing carbon dioxide into organic molecules function best within a moderate temperature range. Above a certain threshold, they begin to work less efficiently, and the rate of carbon fixation drops even though light and carbon dioxide remain abundant. At the same time, photorespiration, a competing process in which oxygen rather than carbon dioxide is processed by the same enzyme, increases with temperature, wasting energy. On the hottest summer afternoons, many plants partially close their stomata and reduce their photosynthetic activity, not because they lack resources, but because the metabolic machinery has reached its thermal operating limit. The green, still quality of a forest on a very hot summer afternoon is partly a physiological response. The trees are not simply standing in the heat. They are managing their internal chemistry carefully, balancing the gains from continued photosynthesis against the risks of overheating and water loss. The biological crust that covers the surface of desert soils in summer is one of the most misunderstood and easily damaged communities of organisms in any ecosystem. This thin layer, which can look like nothing more than a slightly roughened or darkened soil surface, is actually a complex community of cyanobacteria, lichens, mosses, and other microorganisms that bind soil particles together and perform functions essential to the desert ecosystem. In summer, when rainfall is rare and the surface bakes in intense heat, the organisms in the crust enter a state of dormancy, surviving as desiccated but living cells that can rehydrate and become active within minutes of a rain event. When active, these organisms fix atmospheric nitrogen and carbon, adding nutrients to soils that receive almost no organic input from other sources. The crust also resists wind and water erosion, holding the soil surface in place through the summer months when bare soil would be easily moved by wind. A single footstep in the wrong place can shatter decades of biological crust development. The community is slow to recover, and its absence fundamentally alters the hydrology and chemistry of the soil surface. Summer brings the longest days, and for plants at high latitudes, these long days carry a specific biochemical signal that initiates flowering. The length of the dark period in each 24-hour cycle is sensed by a pigment called phytochrome, which shifts between two forms depending on whether it has recently been exposed to red or far-red light. In the long nights of winter, phytochrome accumulates in a form that in many plant species inhibits flowering. As nights shorten through spring into summer, this inhibition is progressively removed. For day-neutral plants, the timing of flowering is governed by temperature and other cues. But for long-day plants, the short summer night is the essential permissive signal. Only when nights have shortened below a critical threshold do these plants begin producing the hormonal signals that redirect shoot growth from leaf production to flower production. The precision of this timing is such that a single night of artificial light during the dark period can delay or prevent flowering entirely. Commercial horticulturists use this knowledge to control the flowering times of chrysanthemums, poinsettias, and other plants by manipulating the length of the dark period with artificial lighting. The smell of summer is largely the smell of volatile organic compounds being released into warm air by an enormous variety of biological and chemical sources. Each source has its characteristic molecular signature. Pine forests release a terpene-rich blend that is sharp and resinous. Freshly cut grass releases green leaf volatiles, short-chain molecules that give the distinctive smell of vegetation being damaged. Flowers release specific blends designed to attract specific pollinators. Warm soil releases geosmin and other compounds produced by actinobacteria. Decomposing fruit on the ground releases esters and alcohols that attract fruit-eating animals. Warm asphalt releases complex hydrocarbons from the petroleum that was used to make it. On a still summer afternoon, when the air is not moving strongly enough to disperse and dilute these signals, they accumulate near their sources. Walking through a summer landscape is walking through an invisible chemical library, each step bringing new compounds to the nose. The human sense of smell, limited compared to those of dogs or insects, nonetheless detects hundreds of distinct compounds, assembling them into the composite experience that the brain categorizes simply as summer air. By the time the deepest weeks of summer have settled around you, the soil has been warm for long enough that its chemistry is entirely different from what it was in spring. The forest has been quietly speaking in molecules for months. The grass has been building its archive of sunlight. The roots have been following their invisible map through the dark. All of that activity is still continuing, right now, in the warmth below the surface and in the air above it. But you do not need to follow it any further tonight. Let it continue without you for a while. The season is long and there is no hurry. Allow the warmth to hold you and the darkness to settle, and let your thoughts drift slowly toward wherever sleep is waiting. Insects navigate summer landscapes using heat as precisely as a map. Many species of bees and wasps can detect infrared radiation, sensing the warmth radiating from dark soil, sunlit stone, or the bodies of flowers warmed by the sun. This thermal sensitivity allows them to locate warm foraging sites before they are close enough to see them clearly. Some parasitic insects locate their hosts by the heat the host body radiates, homing in on the thermal signature of a caterpillar hidden beneath a leaf or buried inside a stem. Dragonflies position themselves in patches of warm air rising from heated ground, using the thermal lift to hover and patrol with minimal energy expenditure. Desert beetles time their activity to the precise window between the time the ground has warmed enough to allow movement and the time it becomes hot enough to be lethal. They run across the surface in short bursts, pausing in the shade of small pebbles to prevent overheating. The thermal environment of summer is not a uniform condition, but a complex and shifting landscape of warm and cool zones that insects read continuously and respond to with navigational precision that rivals any engineered sensor. Birds returning from winter migration arrive into a summer landscape that is timed to match the peak of insect abundance. The coincidence is not accidental. Over thousands of generations, the timing of migration has been refined by natural selection, so that arrival in breeding areas corresponds to the period of maximum food availability. In summer, the insect populations that birds depend on to feed their chicks peak in abundance at the same time that the long days allow more hours of foraging. A summer day at high latitudes can provide 18 or more hours of daylight, giving parent birds an enormously extended window of time in which to collect food for their nestlings. Some species exploit this so completely that their chicks grow at rates that seem impossible by the standards of other seasons. A swift chick in a summer nest in northern Europe may go from hatching to first flight in fewer than 40 days, a transformation powered by the summer insect abundance that its parents harvest during those long, bright days. The long summer day is not merely a backdrop to bird breeding. It is an active resource, a commodity of time that birds have evolved specifically to exploit. The light organs of fireflies produce one of the most energy-efficient light sources found in nature, and summer is the season when they operate. The chemical reaction that produces firefly light converts nearly all of its energy into visible light with almost no heat as a byproduct. An incandescent bulb, by comparison, converts most of its energy to heat, and only a small fraction to visible light. The firefly achieves this efficiency through a precisely controlled enzymatic reaction in which a compound called luciferin is oxidized in the presence of the enzyme luciferase and a molecule of ATP. The light produced is cold, blue-green, and pulsed in species-specific patterns that allow males and females to identify each other across darkened summer meadows. Each species has its own characteristic flash timing, duration, and rhythm. In areas with many coexisting species, the night air in summer can be filled with overlapping flash patterns, each species communicating in its own dialect of light. The females of some species mimic the flash patterns of other species to lure males close enough to capture and eat them. Summer darkness in the right habitat is not empty. It is a medium of biological communication carried out in flashes of cold light. Butterfly wings are thermal management devices as much as they are tools for flight or displays of color. The large surface area of a butterfly wing relative to its mass makes it an effective absorber of solar radiation. On cool summer mornings, butterflies spread their wings and orient them perpendicular to the sun, using the absorbed heat to raise their body temperature to the level required for flight. Some species can raise their thorax temperature by 20 degrees above air temperature through this solar basking behavior, achieving functional warmth in conditions that would leave them unable to fly if they depended on air temperature alone. In the heat of a summer afternoon, the same wings can become a liability. Some species shift their orientation to present a minimal surface to the sun, or move into the shade, or hold their wings in configurations that reduce heat absorption. The color patterns on butterfly wings have thermal as well as visual functions. Dark areas absorb heat more effectively and are often concentrated near the thorax where the flight muscles are located. The elaborate patterns that appear to be purely decorative are partly the result of selection for both optical signals to potential mates and thermal management of the body beneath. Fish in summer rivers and lakes sort themselves through the water column according to a hierarchy of physiological needs. Each species has a preferred temperature range within which its enzymes function optimally, and its immune system operates most effectively. Above this range, metabolic demand increases while oxygen availability decreases, creating a physiological double pressure. Below it, metabolism slows and growth rates drop. In a thermally stratified summer lake, fish position themselves in the layer where temperature most closely matches their preferred range. Trout, which prefer cold water, crowd into the deepest, coldest layer that still contains adequate oxygen. Warm water bass may concentrate just below the thermocline where temperatures are comfortable and prey is available. When summer heat pushes surface water temperatures beyond what any fish can tolerate for extended periods, the fish must choose between acceptable temperature with inadequate oxygen at depth or adequate oxygen with lethal temperature at the surface. These physiological constraints determine the survival of fish populations through summer heat waves more than almost any other single factor. The waggle dance that honeybees perform inside the hive during summer communicates the location of food sources to other foragers with a precision that continues to astonish researchers who study it. A bee returning from a productive flower patch performs a figure-8 movement on the vertical surface of the honeycomb. The angle of the straight portion of the figure-8 relative to vertical encodes the direction of the food source relative to the position of the sun. The duration of the waggling portion of the dance encodes the distance. Other bees following the dance orient their subsequent flight using this information, adjusting for the movement of the sun across the sky between the time the dance was performed and the time they reach the location indicated. The dance is not a fixed message. It is updated as the sun moves and as the food source changes in quality. Bees that have visited the same source multiple times adjust their dancing to reflect changes in the nectar flow. This system of communication, which operates entirely through movement and sound inside a dark hive, allows a colony to allocate its foraging effort across the summer landscape with a collective efficiency that no individual bee could achieve alone. Snakes in summer are so precisely attuned to their thermal environment that their behavior can be predicted from temperature maps of the landscape. As ectotherms, snakes regulate their body temperature entirely through behavior, moving between warm and cool microhabitats to maintain the narrow range of temperatures at which their digestion, immune response, and reproductive physiology function optimally. On a summer morning, a snake emerging from a cool burrow moves to a sun-warmed rock and basks until its body reaches the preferred temperature. It then moves into shade or retreats underground to avoid overheating. After feeding, it seeks a warm location to accelerate digestion, because the enzymatic processes that break down prey function faster at higher temperatures. A snake that is too cold digests its meal so slowly that the prey may begin to decompose before digestion is complete. The thermal landscape of a summer habitat, the distribution of sun patches, shade, warm rock surfaces, and cool underground retreats, is the snake's primary resource map. It reads this map continuously, navigating through the season by following gradients of heat. The songs of male birds in summer carry information about the singer that extends far beyond simple species identification. The complexity, range, and duration of a bird's song reflect its physical condition, its age, and the quality of the territory it holds. Males that have survived multiple migrations and breeding seasons have had longer to practice and develop their songs, and experienced singers tend to produce more elaborate vocalizations than younger males. A female listening to the songs of competing males in a summer territory is effectively evaluating the survival history and current physical condition of potential mates through the medium of sound. The acoustic properties of summer habitats shape how these songs propagate. Dense leaf cover absorbs high-frequency sounds more than low-frequency ones, which may favor lower-pitched songs in forested summer environments. Temperature gradients near the warm ground bend sound upward, reducing the distance it travels at low height. Birds that sing from elevated perches early in the morning, when temperature gradients are minimal and the air is still, achieve the maximum possible transmission of their signal through the summer air. The sounds that fill a summer night in a temperate forest are produced by animals communicating across a medium that summer has shaped specifically for them. The warm air, the dense foliage, the humidity, the temperature gradients near the ground, all of these alter the acoustic properties of the environment in ways that the animals calling through it have evolved to exploit. Crickets and katydids produce sounds by rubbing specialized structures on their legs or wings, generating frequencies that travel efficiently through warm, humid summer air. Each species calls at a slightly different frequency and with a slightly different rhythm, allowing individuals to locate and identify potential mates, even when dozens of species are calling simultaneously. The temperature of the air directly affects the rate at which these insects call. Crickets chirp faster in warmer air and slower in cooler air, a relationship precise enough that the ambient temperature can be estimated by counting chirps per minute. The total acoustic environment of a summer night represents thousands of simultaneous conversations in different frequencies, each directed at a specific audience, each shaped by the physics of sound transmission through the warm and living air of the season. Sea turtles return to summer beaches that may be the same beaches where they hatched decades earlier, guided across thousands of kilometers of open ocean. By a magnetic map, they began constructing as hatchlings. The Earth's magnetic field varies predictably across the ocean, with different locations having characteristic combinations of field intensity and inclination angle. Sea turtles appear to sense both of these parameters and use them to navigate, storing a magnetic address for their birth beach and returning to water with similar magnetic characteristics when they reach reproductive maturity. In summer, the females haul out onto the warm sand after dark, dig nests above the high tide line, and deposit clutches of leathery eggs that incubate through the warmth of the summer weeks. The temperature of the sand during incubation determines the sex of the hatchlings. Warmer sand produces more females. Cooler sand produces more males. The thermal environment of a summer beach is therefore a direct determinant of the sex ratio in the next generation of turtles. Changes in summer beach temperatures caused by climate shifts or artificial lighting that warms the sand alter this ratio in ways that could affect the long-term viability of turtle populations. Frogs and other amphibians manage water loss in summer through a combination of behavioral and physiological strategies that reveal how closely their biology is tied to the thermal and moisture conditions of the season. Amphibian skin is permeable to water in both directions. On a dry summer day, an exposed frog loses water to the air as rapidly as a puddle evaporates, which is why most amphibians are most active at night or during rain. To survive in seasonal climates with dry summers, many species enter a state of summer dormancy called estivation, burrowing into moist soil and forming a mucus cocoon around themselves that slows water loss to a fraction of what it would be in open air. Their metabolic rate drops dramatically, their heart rate slows, and they exist in a suspended state until rain or cooler temperatures signal that conditions have improved. Species that cannot estivate stay near water throughout summer, retreating into it whenever their skin begins to dry. The pond edge in summer, seemingly a place of random frog activity, is actually a carefully managed boundary that each individual navigates according to its current state of hydration and the immediate thermal conditions of the surrounding air. Migratory insects travel through summer air on routes that are encoded genetically rather than learned. A monarch butterfly hatched in late summer in North America has never made the journey to overwintering sites in central Mexico that it will complete over the following weeks. Yet it carries within its nervous system a time-compensated sun compass that allows it to maintain a consistent southwesterly heading regardless of the direction the sun is moving in the sky. The time compensation is critical because the sun's position changes through the day, and a navigator that simply flew toward the sun at a fixed angle would fly in circles. The butterfly's internal clock adjusts the angle of flight relative to the sun as the day progresses, maintaining a consistent compass heading. At night and on overcast days, monarchs can orient using polarized light patterns in the sky that are visible to their eyes even when direct sunlight is blocked. The navigation system is robust enough to produce a successful migration across thousands of kilometers and precise enough to bring millions of individuals to the same small region of forest in Mexico year after year. Summer is when the generation that will make this journey is born, inheriting from their parents a navigational capacity they will not use until the season changes. The pressure changes that precede summer storms are sensed by animals long before any weather instrument in a farmhouse or weather station registers them. Atmospheric pressure drops as a low-pressure system approaches, and this drop can begin hours before clouds appear or wind strengthens. Many insects reduce their activity or seek shelter as pressure falls. Bees return to the hive earlier than usual, and the activity at the hive entrance decreases. Ants seal the entrances to their colonies. Swallows that normally feed high in the air on ascending columns of warm air descend to feed near the surface, following the insects that have been pushed down by the cooler, denser air that precedes a front. These behavioral changes are not learned responses to past experience. They are instinctive reactions to the sensation of falling pressure, refined over millions of years of evolution in environments where failing to take cover before a summer storm could be fatal. Farmers and fishermen throughout history have read animal behavior as a weather forecast, and the animals providing that forecast are responding to physical signals that human senses cannot directly detect. Colony insects manage the internal temperature of their nests in summer through coordinated behaviors that function as a collective thermostat. A honeybee colony maintains the temperature of the brood area, where larvae and pupae are developing, within a narrow range regardless of the temperature outside. When the hive becomes too warm in summer heat, worker bees collect water and spread it in thin films over the capped brood cells, then fan their wings to create airflow that evaporates the water and cools the surface. Hundreds or thousands of bees may be engaged in this collective cooling simultaneously, operating as a biological air conditioning system. Other bees cluster near the entrance and fan outward, creating a directed airflow through the hive that carries heat out. When the hive is too cool, the bees cluster together and vibrate their flight muscles to generate heat without moving their wings. The coordination of these behaviors across tens of thousands of individuals, each responding to local temperature and the actions of nearby bees, produces a colony-level thermoregulation that is more precise than the temperature control available to most solitary animals. Water birds that walk and wade in summer shallows use the physical properties of water surface tension in ways that require careful coordination with the properties of their own anatomy. Certain small birds called jacanas walk across floating lily pads and mats of aquatic vegetation in summer, distributing their weight across enormously long toes that spread their mass over a large area of fragile surface. Other birds exploit the surface tension of shallow water, directly plucking insects from the water film, with bills that create minimal disturbance. Herons stand motionless in summer water, their stillness reducing the bow wave that would alert fish to their presence. When they strike, the movement is fast enough that the fish's nervous system cannot process the warning signal before the bill has already closed. The physics of water, its surface tension, its optical properties that refract images of objects above the surface, its resistance to rapid movement. All of these factor into the feeding strategies that wading birds have evolved over millions of years. Summer, when shallow warm waters teem with prey and long days allow extended foraging, is when these strategies are most actively deployed. Large predators in summer use the thermal properties of the atmosphere to extend their sensory range. Scent molecules released by prey animals rise with heated air during the day and disperse in patterns shaped by wind and terrain. A predator that understands these patterns can position itself downwind of a prey animal's likely location and wait for the thermal-driven scent plume to arrive. Wolves hunting in open terrain in summer have been observed positioning themselves to use wind and terrain features in ways that suggest an understanding of how scent travels through the landscape. Bears use their extraordinary sense of smell to locate food across distances of many kilometers, following scent gradients that are shaped by the thermal structure of summer air. The daily heating cycle matters to predators because the rising air of midday disperses scent upward and reduces horizontal transmission, while the cooling of evening allows scent to sink and spread along the ground. Predators that adjust their hunting to the thermal cycle of the summer day are exploiting a real physical phenomenon, using the atmospheric physics of the season to extend what their senses can reach. Nocturnal mammals in summer must navigate a thermal landscape that is the inverse of the daytime one. While the daytime surface is hot and dangerous for small, poorly insulated bodies, the night surface cools rapidly, and the deep warmth retreats underground. Many small mammals exploit a thermal window in the early evening when surface temperatures have dropped to comfortable levels, but the cold of deep night has not yet arrived. Desert rodents time their activity precisely to this window, emerging from burrows, foraging intensively, and retreating before temperatures drop far enough to threaten them with hypothermia. In cooler regions, the thermal window is wider and less precisely bounded, but the principle is the same. Activity is concentrated in the period of most favorable thermal conditions, and the length and timing of this window changes through the summer season as nights grow longer and cooler toward autumn. Summer nights, which begin short and warm and gradually lengthen, represent a shifting resource for nocturnal mammals, a slowly expanding window of safe activity that tracks the changing season week by week. The responses of marine mammals to summer sea surface temperature changes reveal the precision with which large animals track environmental gradients. Whales feeding in summer polar waters follow the distribution of krill and small fish, which in turn follow the thermal fronts where cold, nutrient-rich upward water meets warmer surface water. These fronts, visible from satellites as sharp boundaries in sea surface temperature maps, concentrate prey on one side while providing the physical conditions that aggregating prey require. Whales that navigate to these fronts are using information encoded in the temperature structure of the ocean, information that is only available during summer when the contrast between warm and cold water is strongest. In summer, the thermal structure of the ocean surface is a map of biological productivity, and the animals that can read this map travel hundreds of kilometers to find the most productive patches. The summer ocean is not uniform. It is a thermally organized landscape, and the animals that live in it navigate its structure as precisely as any terrestrial animal navigating a physical terrain. As the warmth of this long summer night settles around you, and the details of all those living things pursuing their invisible strategies begin to soften and blur, There is nothing left to follow. The bees have returned to their hive. The fireflies have completed their last flash of the evening. The turtle has covered her nest with sand and returned to the sea. Let them continue without you. The summer night is wide and unhurried, and there is nothing it requires of you now except to rest. Metals in summer expand with a consistency that engineers must account for in every large structure they design. As temperature rises, the atoms inside a metal vibrate more energetically and push against their neighbors with greater force, causing the material to occupy more space. The amount of expansion varies by metal type, but is predictable enough to be calculated precisely for any given temperature change. Steel bridge spans can be tens of centimeters longer on a hot summer afternoon than on a cold winter morning. Railway tracks laid without adequate gaps between sections would buckle and distort under summer heat, pushing sideways against each other as they expand with nowhere to go. Engineers design expansion joints into bridges, railways, pipelines, and buildings specifically to accommodate this seasonal movement. The joints allow the structure to grow and shrink freely without generating destructive internal stresses. In very long structures like suspension bridges, the cables themselves lengthen in summer heat and shorten in winter cold, causing the road deck to sag slightly lower in summer. The geometry of a large bridge changes measurably between seasons, a slow breathing that is invisible to anyone crossing it, but essential to its survival over decades. Summer heat changes the behavior of bridges, buildings, and roads, not just through the expansion of their materials, but through the differential expansion of different materials in contact with each other. When two materials with different thermal expansion rates are joined together and then heated, the material that wants to expand more is restrained by the one that expands less. This creates shear stress at the joint between them. In reinforced concrete, the steel reinforcing bars and the concrete surrounding them have similar enough expansion rates that they work together successfully through normal temperature ranges. But at extreme summer temperatures, or after many cycles of heating and cooling over years, the cumulative stress can cause cracking in the concrete around the reinforcing bars. In composite structures where steel and concrete are joined to act together, the engineers must calculate the forces that develop at the interface as the materials respond differently to summer heat. Glass installed in window frames expands at a different rate from the metal or wood of the frame, which is why glaziers leave small gaps and use flexible sealants that can accommodate the relative movement. The invisible stresses that build up inside structures on hot summer days are a continuous engineering challenge, managed through careful design and material selection, rather than ever fully eliminated. Asphalt in summer behaves more like a very slow liquid than a solid. The bitumen that binds the aggregate in road surfaces has a glass transition temperature, a point below which it is brittle and glassy, and above which it becomes increasingly plastic and deformable. In cold climates, this transition occurs near or below typical winter temperatures, which is why cold pavement cracks under the stress of heavy vehicles. In summer heat, asphalt softens toward the plastic end of its behavior range. Under sustained load, it creeps, deforming slowly but measurably in the direction of the force applied. The ruts that develop in heavily trafficked roads in summer, the grooves worn by the wheels of trucks following the same path day after day, are the result of this slow plastic flow. The deformation is cumulative. Each vehicle contributes a tiny permanent change, and over a summer of heavy traffic, the surface can develop ruts deep enough to affect vehicle handling and drain water poorly. Road engineers select asphalt mixtures with properties matched to the expected summer temperatures of the region, using stiffer, harder bitumen in hot climates and softer formulations where winters are severe. Glass surfaces in summer accumulate heat in ways that create unexpected microclimates directly adjacent to buildings. A south-facing glass wall or a greenhouse receives solar radiation and transmits much of it inside, where it is absorbed by the contents and converted to heat. The air inside a glass structure on a summer day can reach temperatures far above ambient air temperature, a phenomenon that gardeners exploit for growing heat-loving plants, and that can be dangerous if animals or people are confined inside. On the outside of a glass building, reflected sunlight from large glass facades can create hot spots on the surrounding streets and sidewalks, concentrating solar radiation in areas where pedestrians walk. Architects in hot climates must design for this effect, using shading, orientation, and glass coatings that reduce solar transmission to prevent buildings from overheating and from creating uncomfortable conditions in the surrounding area. The interaction between summer sunlight and glass is one of the primary thermal engineering challenges in warm climate construction, and getting it wrong can make a building unpleasant or dangerous to occupy, even when the temperature outside is moderate. Lightning in summer carries an electrical current that briefly makes the air around it hotter than the surface of the sun. The physics of lightning formation involves the separation of electrical charge in a developing thunderstorm, the accumulation of enormous potential differences between regions of opposite charge, and the sudden formation of a conductive plasma channel when the field becomes strong enough to ionize the air. The return stroke that travels up the channel to the cloud is completed in a fraction of a millisecond, but carries a peak current of tens of thousands of amperes. The rapid heating of the narrow air channel to temperatures around 30,000 degrees causes explosive expansion, creating the pressure wave that travels outward as thunder. Lightning also produces nitrogen oxides by forcing atmospheric nitrogen and oxygen to react at these extreme temperatures. These compounds are washed into the soil by rain, where they contribute nitrogen that plants can absorb. Summer thunderstorms therefore perform a dual function in the chemistry of the landscape, delivering both water and a small but measurable contribution of fixed nitrogen to the ecosystems below. The lightning bolt is not merely a dramatic spectacle. It is a chemical event that connects the physics of the atmosphere to the biology of the ground. Wind patterns in summer differ from winter patterns in ways that reach from the surface of the ground to the edge of the stratosphere. The jet stream, a high-altitude river of fast-moving air that encircles the planet, shifts northward in the northern hemisphere summer as the thermal contrast between the equator and the poles weakens. This shift moves the storm track northward as well, bringing fewer frontal weather systems to mid-latitude regions that are instead dominated by the dry, stable air of high-pressure systems. Surface winds in summer are often weaker than in winter because the pressure gradients that drive them are less steep. The sea breeze and land breeze cycles become the dominant wind patterns in many coastal regions, their rhythms set by the daily heating and cooling of the land. In the tropics, the summer monsoon reverses the wind direction across entire continents as the heating of large land masses draws moisture-laden air in from the ocean. The Asian monsoon, driven by the intense heating of the Tibetan Plateau and the surrounding land masses, is the largest single atmospheric circulation feature driven by summer heating, delivering rainfall that billions of people depend on for agriculture and water supply. The absence of snow cover in summer fundamentally changes the energy balance of the land surface across enormous areas. Snow and ice are among the most reflective surfaces on Earth, returning the majority of incoming sunlight back into space. When snow melts in spring and the bare or vegetated ground is exposed, the surface becomes darker and absorbs more solar energy. This shift in reflectivity, called albedo, amplifies summer warming. The darker the exposed surface, the more heat it absorbs and the warmer it becomes. In the Arctic, where sea ice has been declining in recent decades, the replacement of white ice with dark open ocean in summer has created a powerful feedback that accelerates warming in that region far faster than the global average. The open water absorbs heat through summer, which delays the refreezing of ice in autumn, which means more dark ocean is exposed the following summer. The seasonal transition from snow-covered to snow-free land and sea is one of the most significant events in the annual energy budget of the planet. And summer is when this transition has its maximum effect on how much solar energy the Earth absorbs. Tropical cyclones draw their energy from the warm surface of the summer ocean in a process that is as elegant as it is destructive. As a developing storm system moves over water that is warm enough to sustain intense evaporation, it draws enormous quantities of water vapor into its circulation. This vapor rises in spiral bands of cloud, cools, and condenses, releasing the latent heat stored when the water evaporated from the ocean surface. The released heat warms the air in the rising column, reducing pressure at the surface and drawing more air inward along the surface of the ocean. This inflow evaporates more water, which rises and condenses and releases more heat, which draws more inflow. The storm is a heat engine running on the temperature difference between the warm ocean surface and the cold upper troposphere. As long as it remains over sufficiently warm water and is not disrupted by wind shear in the upper atmosphere, it can intensify continuously. Summer provides the necessary warm ocean surface temperature because months of sunlight have heated the water to depths of several tens of meters. When a tropical cyclone crosses onto land or over cooler water, it is cut off from its energy source and weakens rapidly. But the damage it delivers in its hours of landfall can reshape coastlines and ecosystems for years. Heat changes the mechanical properties of rock through a cycle of expansion and contraction that operates on every exposed stone surface every summer day. As the sun rises and heats the outer layer of a rock face, that layer expands. The rock beneath it, still cool, does not expand at the same rate. This differential expansion creates stress at the boundary between the warm outer layer and the cool inner mass. The stress builds through the morning and into the afternoon as the surface temperature climbs. In the evening, as the surface cools, it contracts while the interior is still warm from the day's absorbed heat. The stress reverses direction. Over thousands of repetitions through many summers, this alternating stress weakens the bonds between mineral grains in the outer layer, causing thin sheets to spall away from the surface. This process, called insulation weathering, is most active in summer in continental climates where daytime temperatures are high and nocturnal cooling is pronounced. The breakdown of rock by summer heat, combined with the chemical weathering accelerated by warm water, produces the mineral particles that form the basis of soil. Summer is not just a season of biological growth. It is a season of geological transformation, converting solid rock slowly and persistently into the raw material of landscapes. Sand dunes in desert regions migrate measurably through summer as wind moves dry particles across the surface. Sand grains are lifted from the surface by wind, carried through the air for a short distance, and deposited slightly downwind. The downwind face of a dune receives this deposited sand and grows steeper until the angle becomes unstable, and avalanches of sand cascade down the slip face. The entire dune moves in the downwind direction through this process of erosion on the windward face and deposition on the leeward face. The rate of migration depends on wind speed, sand grain size, and the moisture content of the sand. In summer, when desert sands are completely dry, migration rates can be fast enough to bury roads, infrastructure, and vegetation within a single season. Communities in and near deserts have developed strategies for managing this seasonal sand movement, including planting windbreaks, spraying oil or water to stabilize surfaces, and constructing barriers that disrupt wind flow. The dunes themselves are in constant slow motion through summer, their shapes maintaining a characteristic form, while their substance is continuously replaced as grains arrive on one side and depart from the other. The cracking of summer soil as it dries reveals a geometry that is determined by the physics of tension in a shrinking sheet of material. When wet clay soil loses water, it shrinks. The surface layer dries and shrinks first, while the deeper soil is still moist and relatively unchanged in volume. The shrinking surface layer develops tension, and when this tension exceeds the tensile strength of the soil, it cracks. The cracks form a network of polygons, with the spacing between cracks determined by the depth of the drying layer and the mechanical properties of the soil. In heavy clay soils with high shrinkage capacity, summer drought can open cracks wide enough to insert a hand and deep enough to extend a meter or more into the ground. These cracks alter the hydrology of the soil dramatically. When rain eventually arrives, water flows directly into the cracks and reaches deep soil layers that it would otherwise take weeks to penetrate by slow percolation. This rapid deep wetting can trigger renewed biological activity at depth, while the surface is still dry and cracked. The cracked summer soil surface is not simply damaged terrain. It is a seasonal structure that shapes how water moves through the landscape when the drought finally breaks. Urban areas in summer generate and retain heat through mechanisms that have no parallel in natural landscapes. Streets, buildings, parking lots, and rooftops absorb solar radiation during the day and release it slowly through the night, maintaining temperatures significantly above those in surrounding rural areas. This urban heat island effect is strongest in summer when solar radiation is most intense and most persistent. The lack of vegetation in dense urban areas removes the cooling effect of transpiration. The canyon geometry of streets between tall buildings traps long-wave radiation that would otherwise escape to the sky. Dark surfaces absorb more heat than the lighter natural surfaces they replaced. Air conditioning units exhaust heat into the urban atmosphere while cooling the interiors of buildings. The cumulative effect can raise summer night temperatures in the urban core by several degrees above the surrounding countryside. For residents without access to air conditioning, these elevated night temperatures prevent the physiological recovery that cooler nights would allow, increasing the health impact of summer heat waves. The urban heat island is an unintended thermal engineering project, the collective result of millions of individual design decisions that were never evaluated for their combined effect on the summer thermal environment. Electricity demand in summer follows a pattern driven almost entirely by the physics of heat and the human response to it. As temperatures rise above a threshold of roughly 24 degrees in most temperate climates, the use of air conditioning increases sharply. Each additional degree of temperature above this threshold drives a measurable increase in electricity consumption. On the hottest summer days, electricity grids experience their annual peak demand as millions of air conditioning units operate simultaneously, attempting to maintain interior temperatures below the level that causes discomfort or physiological stress. Power plants that generate electricity also operate less efficiently in summer heat because they depend on cool water for their cooling systems, and summer river and lake temperatures reduce the efficiency of heat rejection. The combination of peak demand and reduced generating capacity creates the conditions for electricity shortages on the hottest summer days. Grid operators manage this by scheduling maintenance for cooler seasons, importing power from neighboring regions, and in extreme cases, reducing voltage across the grid to decrease demand. The summer heat wave is simultaneously a human comfort problem, a physiological health challenge, and an engineering test of the electrical infrastructure that modern society depends on. The summer solstice, the moment when the sun reaches its highest point in the sky and days are longest, is not the hottest time of the year in most places. Peak temperatures typically occur weeks after the solstice, a phenomenon called the lag of the seasons. The reason is that the land and especially the ocean require time to absorb and store the heat arriving from the sun. At the solstice, the rate of solar energy input is at its maximum, but the accumulated heat stored in the ground and water is still below its annual peak. It takes weeks of continued heating for the stored heat to build to the point where it produces the warmest temperatures. The ocean lags especially far behind the solstice because of its enormous heat capacity. Coastal regions that are moderated by the ocean experience their warmest temperatures in late summer or early autumn, weeks after inland areas have already passed their peak and begun cooling. This thermal lag is the same reason that the coldest part of winter typically comes weeks after the winter solstice. The calendar date of maximum or minimum sunlight does not coincide with the calendar date of maximum or minimum temperature, because the land and sea are not passive thermometers, but enormous heat reservoirs with their own response times. High-altitude regions experience summer in compressed and intensified form. At 3,000 meters above sea level, the atmosphere above is thinner and contains fewer molecules to scatter and absorb incoming sunlight. Ultraviolet radiation is significantly more intense than at sea level, and the air temperature drops with altitude at a rate of roughly 6 degrees per 1,000 meters on average. The combination of intense radiation and cold air creates conditions that have no equivalent at low elevation. Snow can exist within meters of vegetation actively growing in intense sunlight. Insects are active in the middle of the day because that is when the air temperature is warm enough for their metabolism to function, and they must complete their activity in a narrow thermal window that closes when the sun passes behind a ridge or a cloud. Alpine flowers bloom and set seed in a compressed season that may last only a few weeks. The growing season at high altitude is summer reduced to its essence, a brief intense window of warmth and light surrounded on all sides by conditions that would suppress biological activity entirely. The atmosphere above summer thunderstorms reaches into the stratosphere in a process that has consequences for chemistry at altitudes far above where the weather is happening. In exceptionally powerful convective storms, updrafts can be strong enough to punch through the tropopause. the boundary between the troposphere and the stratosphere, and inject water vapor, aerosol particles, and chemical compounds into the lower stratosphere. This process, called overshooting tops, carries material from the surface and the lower atmosphere into a region where it would not normally arrive because the stable stratification of the stratosphere resists vertical mixing. Once in the stratosphere, these injected materials can remain for months or years, slowly spreading around the globe with upper-level winds. Water vapor injected into the lower stratosphere contributes to the formation of stratospheric clouds that participate in chemical reactions affecting ozone. Aerosol particles affect how much sunlight the stratosphere transmits. Each large summer thunderstorm is therefore not merely a local weather event. It is a small but real contributor to the chemistry of the atmosphere at altitudes where the sun's influence on the planet's energy balance is determined. Bioluminescent waves on summer beaches are produced by a community of organisms whose light is triggered by mechanical disturbance in a way that has several possible explanations, none of which is fully settled. When a wave breaks and the turbulence disturbs the dinoflagellates concentrated near the surface, each cell responds to the mechanical stress by opening ion channels in its membranes, triggering a chain of chemical reactions that produces a flash of blue light lasting a fraction of a second. The flash is fast, bright relative to the organism's size, and produced at minimal metabolic cost relative to the information it might convey. Some researchers have proposed that the light startles potential predators, giving the dinoflagellate a chance to escape. Others suggest that the light attracts larger predators that eat the zooplankton consuming the dinoflagellates, a kind of biological alarm call that summons help. Still others note that the light may simply be an unavoidable byproduct of the chemistry involved in a stress response that has other primary functions. The glowing summer wave that looks like magic from the beach is the aggregate output of billions of single-celled organisms, each responding individually to the mechanical force of a breaking wave, each adding one tiny flash to the collective display. The cooling effect of a summer breeze on human skin involves physics that operates at the molecular level. Air moving across the skin carries away the water vapor that evaporates continuously from its surface. Still air near the skin becomes saturated with water vapor and reaches equilibrium with the skin's surface, slowing further evaporation. Moving air sweeps this saturated layer away and replaces it with drier air, allowing evaporation to continue at a higher rate. Since evaporation requires energy, and that energy is drawn from the skin's surface as heat, a breeze cools the skin by accelerating the evaporation of moisture from it. This is why a summer breeze feels cool even when the air temperature is above body temperature. The air itself is warmer than skin, but it is removing heat through the mechanism of evaporative cooling faster than it is adding heat through convection. At very high humidity, when the air is already nearly saturated with water vapor, a breeze provides less cooling because there is less room for additional evaporation. The oppressive quality of hot, humid summer air is the physical reality of a cooling mechanism that has been largely disabled by the water vapor already present in the atmosphere. The breeze still arrives. It simply cannot do what it does in dry heat. Summer nights carry their own distinct physics that separates them from summer days more completely than the simple absence of sunlight suggests. After sunset, the ground begins to radiate the heat it has accumulated through the day back toward the sky as infrared radiation. This process cools the surface. Clear nights allow this radiation to escape freely into space, and the surface cools rapidly. Cloudy nights trap the outgoing radiation and reflect it back toward the surface, keeping temperatures higher. The difference in overnight cooling between clear and cloudy summer nights can be 5 degrees or more. Dew forms when the surface cools below the dew point. Fog forms in valleys and low-lying areas where the cooling is most intense and moisture accumulates. Small animals that were sheltering from the heat of the day emerge into an environment that is physically different from the one they retreated from. The air near the ground has cooled. The scent landscape has changed as volatile compounds behave differently at lower temperatures, and the acoustic environment has shifted as temperature gradients change the paths of sound waves. Summer night is not simply summer day with the lights off. It is a physically distinct environment, created by the same forces that made the day, now operating in reverse. In the deep quiet of late summer, when the season has run its full course and the days are beginning to shorten almost imperceptibly, the landscape carries the accumulated record of everything that happened since spring. The rings inside the trees are nearly complete. The birds have raised their young, and in some species have already begun the subtle preparations for departure. The soil has processed months of fallen organic matter and returned it to the cycle in new forms. The ocean has stored its warmth and will release it slowly through the coming season, moderating the approach of autumn in coastal regions, the way a large stone holds the warmth of the day into the evening. All of this has happened continuously, quietly, without announcement, driven by the same physical laws that operate in every season, but expressed in the particular forms that only summer makes possible. The warmth, the light, the length of days, these are not simply conditions that life endures. They are conditions that life has shaped itself around over hundreds of millions of years, evolving specific strategies, biochemistries, and behaviors that are keyed precisely to what summer offers and demands. The season is not background. It is a participant, shaping every living thing that passes through it and being shaped in return. You have traveled through some small part of that story tonight. The rest of it continues without pause in every direction, and it will still be continuing when you wake. As the last of these summer facts drifts past you and the details begin to soften into something without edges, there is nothing left to hold on to and nothing that requires your attention. The atmosphere has finished its chemistry for now. The trees have pulled their water upward for the last time today. The fireflies have gone dark. The waves on the warm shore have settled into their slow rhythm with no one watching. You have traveled through the whole quiet machinery of summer tonight, and all of it can fade now into the background like heat rising from the ground on a still afternoon, visible for a moment and then gone. If this journey brought you some peace, the Learn When You Sleep channel would be glad to have you back. But for now, there is nothing left to do. The summer night is long and unhurried, and it asks nothing of you except to let go. Good night.